Hey, so let's talk a little bit about reactions here. The two main energy requirements I need you to know are that there's an exothermic and an endothermic reaction. An example of an exothermic reaction is when energy is released. So, when we did the magnesium and oxygen reaction as part of our lab, where we lit the magnesium on fire, that was considered an exothermic reaction because after a little bit of activation energy, every reaction needs a push, there was a whole lot of energy released. The same would be true if we combined hydrogen and oxygen. What was the other? Oh, so and if we use those little hand warmers in class, making those hand warmers release that heat would be exothermic. So exothermic reactions, even though they require a little bit of activation energy, at the end of the day, your starting material or reactants is going to go downhill to a lower energy product. And that's what all exothermic reactions have in common. So energy is sort of like the product. Even though we say here it's a negative number, that's because energy is released after this reaction takes place. So you're going from a higher energy level to a lower energy level, hence the negative number. Endothermic reactions is the opposite. The activation energy basically is the majority of the energy in the reaction. So when we turned water into its component parts with the battery that I hooked up, that took a whole lot of energy to get up there. And because of that, energy is like a reactant. You're having to put energy in, and the difference between the height of the starting material and the products is going up in energy. So if this is your energy, you're increasing your energy going from reactants to products. So the activation energy is much larger for an endothermic reaction than it would be for an exothermic reaction, as you can see here. It doesn't require near as much activation energy. So when we were discussing how reactions are reversible, this is the case. So with a lot of energy, you can turn hydrogen into its components. With just a little energy, you can release a bunch of energy when hydrogen and oxygen come together. Um, we'll talk about that later. Right now, I want to make sure that we get this. Driving forces are reactions, uh, the reason why reactions proceed forward. So, an example here is if you form a gas, if you form a solid, or if you make water. So, the water one works really well for what we call an acid base reaction. You have H plus and OH minus coming together to do water. But let's talk about these predicting reactions based on this chart. So you will always be given this chart. Please don't memorize it. And what you should realize is the stuff down here, silver, platinum, gold, this is jewelry, right? So the reason these are in jewelry is because these things don't react. They're very stable. And so you can wash your hands or work on your car and you're still not going to lose that piece of metal if it's a ring or a bracelet or whatever. Whereas things up here tend to like to be ions. They react. And so lithium is in batteries, and the potassium that you know in bananas is already an ion. It's K plus, and the calcium that you know to be in milk is already an ion. It's Ca2 plus. So this chart is very helpful in trying to predict what will happen. So for example, here's calcium. There's calcium. And calcium is in a situation where it's an ion. This is the +2 ion because each of these fluorines is -1. And then the question is, if that were going to be paired up with zinc, would something happen? Would there be a reaction? Well, zinc compared to calcium is more stable. So down here you have the stable things, right? These are more stable as metals. And up here you have things that want to be ions, right? So that's already an ion. Calcium is already a +2 ion. Zinc is here as 0, so it's not an ion. But calcium wants to be an ion more than zinc, so there would be no reaction here. And that's the kind of stuff I'm expecting you to know. So silver nitrate, silver being down here, this is in the +1 form because it's with nitrate, which is -1, and magnesium, which is higher. So now magnesium, since it's higher than silver, is going to want to change places with that silver. So magnesium would go to magnesium nitrate, and the silver would come out. And this is an example of what we did in the reactions lab again, because silver would rather come out and be Ag0. It's going to change places with that magnesium. So there would be a reaction here. So some more examples here. If silver gets together with zinc, All right, so silver being down here and zinc is above it. Oh wait, no, it's not the same thing. So silver with zinc. Hopefully you realize zinc would rather be in the ion. Here it is with an ion. It's +2 with the two bromines, which are -1. Silver is 0. So nothing's going to happen here. Silver is happy to be 0. It's not going to react. Um, that's why, again, we use it for jewelry and such. So that would be no reaction. When aluminum and strontium get together, though, aluminum is right here. Strontium is higher than aluminum, so it would rather be an ion. Here it is not an ion, it's at 0. So the aluminum strontium would change places, and we would get strontium nitrate, and aluminum would come out. So as far as that goes, hopefully you realize strontium, where it is on the periodic table, is +2. Let's discard that. But yeah, hopefully you realize, right? Hopefully you all realize that strontium is right here. So it's +2, right? It's in that +2 chain where it loses 2. Anyway, all right. So aluminum and acid, if you look back on this thing, aluminum here is in a situation where it says will react with hydrogen from acids, right? All of these here react with hydrogen from acids, and aluminum's in that. So in fact, if you've ever had this situation where aluminum foil will stick to an acidic dish, like some tomato-based things which have acid in them, might start reacting with that aluminum. And if you ever cook with vinegar on a, if you use a vinegar-based marinade for your steak and then wrap it in aluminum, put it on the grill, you'll see that the aluminum starts getting eaten away because the acid in the vinegar. Anyway, all right, so tin versus aluminum here. Tin is below aluminum. So again, remember, these want to stay, so these are not ions down here. They like to be 0. So here, tin is 0 and aluminum is +3 because it's with the chlorine. So aluminum wants to be an ion, so that would be no reaction. It's happy the way it is. The aluminum would not want to be 0. Magnesium, which is up high, right above aluminum, and acid, which is right here. So all of these also represented by hydrogen. Well, in this case, magnesium would rather be the plus than the hydrogen. So you would get MgCl2 and H2 as a result of that, because the hydrogen would rather be by itself and the magnesium would rather be with something as an ion. So remember, these like to be ions up here. So this is the kind of thing I'm going to expect you to do. I don't know why I have that right there. But I guess we weren't going to deal with that. Okay. So then the other reaction we did, the double replacement. Remember, if we had something like sodium chloride and silver nitrate, if the silver gets together with the chlorides, right, and comes out a solution, which is what happens here, then we say a reaction occurred because we see that solid. So here's a solid. If, however, if we had potassium hydroxide and sodium chloride, so here's the sodium chloride, here's potassium hydroxide, they don't want to come out of solution. So there's no issue here with sodium hydroxide and potassium getting with the chloride. Nothing happens. They all just stay floating around in solution. And because of that, we say that there's no reaction. So when you're doing these double replacement reactions, the thing you're going to want to do is switch out your metals, your first things listed. So here, calcium will get together with the sulfate, and the potassium will get together with the nitrate. And as a result of that, you need to just consult this chart and see if anything is going to go into solution or not. Now remember, the word AQ, or this abbreviation, means it'll dissolve in water, and I here means insoluble, or it won't dissolve in water. So here we're looking for calcium sulfate. Well, calcium sulfate, well, here's calcium, and here's sulfate. And if you go to the place where calcium and sulfate, you would see there that it's insoluble. So this would actually form a solid, and that means a reaction is going to occur. If you look at potassium and nitrate, potassium's up a little higher, nitrate's one of the first ones. So those meet here at aqueous. So that would be an aqueous solution. So even though this is aqueous, because this is a solid, we would say a reaction would occur because it's a solid. And as we saw in our reaction thing, that means something would form here at the bottom of the reaction. All right, so copper nitrate and iron sulfate. So we're going to again switch our metals. So copper will now be with sulfate, and and the iron will be with the nitrate. And then we're going to look here, and the iron with the nitrate is aqueous. All right, even if you didn't know this was iron 2, it's or iron 3, either one's aqueous, so it doesn't matter. So this thing is aqueous, but we know it's iron 2 because SO4 is a -2, and that iron is 1 to 1 with that. Copper sulfate. So copper is here, sulfate is here. So that's aqueous. So that means nothing's going to happen in this reaction. Both of these are still going to be swimming around, and it's going to look like this. It's going to be a clear solution, and then you mix them and you still get a clear solution. So nothing happens because nobody gets together. There is no precipitate. There is nothing insoluble. So again, you will have this chart. There's no reason to memorize that. And you will be able to do this. So again, with double replacement, you're going to just switch out your metals. So the sodium will be with the nitrate, and your barium will be with the sulfate. And then you're just going to have to look on this chart and see what happens. So barium with sulfate is insoluble, and sodium with nitrate is aqueous. So that one, this one is aqueous, but this one is a solid, and that means that a reaction occurs. So potassium with silver, potassium acetate, silver nitrate, those will switch places, and if you consult your potassium nitrate will be soluble, as will your silver acetate. So if we look here, silver acetate, here's silver. Oh no, silver acetate is not soluble. It's insoluble. There you go. Learned something there. But the potassium nitrate is soluble. So when those two get together, this will be solid because it's insoluble, and this will be aqueous. So that means a reaction occurs. All right. Lead and potassium. So lead will be with the iodide, and the potassium will be with the nitrate. We know the lead is +2 because it takes 2 nitrates, and if for any reason you forgot that, right here it tells you nitrate is -1. So lead, I don't remember what we're doing now. It's lead iodide and potassium nitrate. So lead is, where's lead? Oh, lead iodide is insoluble, so that would make the solid. And the other one, potassium nitrate, so this is a solid. That means a reaction is going to occur. And potassium nitrate, just like here, is going to be aqueous. All right, so again, with these, you're just comparing whether the thing up here, which wants to be an ion, is an ion, and the thing down here is, wait, do I want to do that? No, I don't know. Yeah, that should be good. All right, so work on that. There's homework. You can check answers. And that's all I talked about.